Okay, let's move on to the lecture of today, and it's got to do with this, I'll call it a thing for now. It's called a tesseract or a hypercube. Okay? And maybe a lot of you have heard about it. Okay, it comes really from relativity. Okay, because it's identified or associated with space-time, which is also a four-dimensional. Again, for lack of a better word, I'll say thing, four-dimensional thing called space-time, within which we live. We live within this box known as space-time. Okay, and so yeah, these notions are concepts are related. Okay, so let's see. What I'm going to do is I'll drive it through again comments that people made, specifically one individual who wrote quite a bit, and I think each point was well taken. In other words, needs to be addressed. Okay? So here it goes. We'll put this man in the spotlight. Okay? Here it goes. Okay, this gentleman says, a sphere is an object. We start with sphere, okay, because we need to find out, what how the reasoning goes, okay. It says a sphere is an object we can see and touch. Okay, that's why he thinks it's an object, because you can see it and touch it, and that's what most people out there think an object is, that which you can see and touch. This is the ordinary notion that most people have out there. If you ask anyone on the street, that's probably what they'll tell you. What is an object? Well, it's what I can see and touch. I can see and touch the table, so that's an object. That's the notion people have out there. And in fact, that is the definition we find in the dictionary, the ordinary dictionary. And it turns out it's also a synonym of the word exist, because when you ask someone, well, what do you mean by exist, that this table exists? He says, well, I can see and touch it. So the word exist and the word object or thing, entity, medium, whatever you want to call it, all these synonyms, they're synonyms. Exist and object are synonyms in the minds of all people out there. Okay, and we try to correct that. We have a different definition. Okay? And he says, okay, it is three-dimensional. Okay, true, a sphere is three-dimensional. And he says it can be weighed or measured. Weighed or measured? A sphere is an ideal geometric object. It should be, at least. That's what we think it is. That's what the word sphere has always more or less been alluded to. Okay, and so, when you look at a sphere, you look at something that looks like a ball, something like that, similar to that, but it's a perfectly smooth geometric object. In other words, it's an ideal geometric object because we cannot produce anywhere in the universe a perfect sphere. If you go in there with with God's eyes and you look at it with your magnifying glass, you'll see some imperfections. So there is no such thing as a perfect sphere out there in the universe. Therefore, you cannot weigh it, you cannot touch it, and you cannot measure it, because there is no such it out there. Okay? So no, a sphere cannot be touched or seen or weighed. But see, we got another issue here, and that's this. Okay, that according to mathematical physics, which is what I've discussed last time, a sphere is what is it? It's the twirling of an itinerary. You do an itinerary, which is known as a circle, which is just a bunch of locations. Okay, you cut that itinerary in half, that circular itinerary, you cut it in half and you have what is known as a semicircle. And then what you're going to do, you're going to twirl that semicircle, which is just a bunch of locations, and that's known as a sphere according to all those sources that you see there. And I've discussed that last week, so you can check on that. Okay, so no, a sphere is not an object according to mathematical physics, according to formal geometry. No, a sphere is what you're seeing there, just a twirling of a bunch of locations. In other words, of an itinerary. Okay, in fact, half a circle, which is a circle. What is a circle? A bunch of locations. Okay, now here's the other issue, and that is, can this individual see or touch the sphere that the Klingon has, who lives gazillions of light years away? Can you see or touch that sphere? Hopefully the answer is no, unless you're superhuman, and I do envy your eyesight if you can see it, and I envy your long arm of the law that you can stretch your hand all the way to that sphere and touch it. So if you can't see or touch the Klingon's sphere, is that sphere a physical object? I mean, for him it is, but is it for you? And so we get into this thing where, it comes down to opinions, and, it's like, it depends on subjectivity. Is his sphere an object for you? Does that sphere exist? If exist is defined as see and touch. Okay, so this is the issue, and so this is the question this gentleman has to answer. Okay, Here's another issue in what this gentleman raised. Let me see if I can put this back up here. If I can find it. I think it's this one. Yeah. This is a second issue. Okay, here it goes. And it's the word surface that he's got in that second line. He says, its surface is two-dimensional. Well, what I see there is that its surface is three-dimensional. You know, I see that the entire surface, you know, even, but what is a surface? You know, a surface is the ball without its center. Okay, without anything in the center. It's just the skin of the ball, so to speak. And that skin is three-dimensional. It's got length, width, and height. So I don't know what he means by that the surface of that sphere is two-dimensional. So that's something he's got to clarify. Now, in science, it's that's a three-dimensional skin or membrane or whatever. And here you look up the word surface. This is out of the Wikipedia. It says the outer face, outside or exterior boundary of a thing, outermost or uppermost layer or area. The problem is that they use these synonyms known as face and area. And when you look them up, you know, they're just synonyms of the word surface. So we don't know what they said when they said it's the face, the outside area or whatever. And then you have exterior boundary. You look at boundary, it says the farthest limit of an area, border. And if you use the boundary of a three-dimensional object, such as a sphere versus a two-dimensional plane, like a circle, well, those boundaries are not the same. They're not the same notions, okay? So the word boundary needs to be defined as well a little more precisely so that we know what they mean by surface. And of course, what this shows is that mathematical physics never defined words scientifically. Never. There's not a single definition which is scientific in all of mathematical physics. Okay? And here's another definition of surface. This comes from I think it's the Wikipedia, yeah, again. And it's got this set of definitions. So let's go quickly through them. It says, surface area of a solid object is a measure of the total area that the surface of the object occupies. Okay, we're talking about volume here? I don't know. Is that what surface area is? The amount of water the rubber ducky displaces? It says this definition of surface area is based on methods of infinitesimal calculus and involves partial derivatives and double integration. What does mathematics have to do with the question before us? We're trying to figure out what a surface area is from physics point of view. We're not trying to calculate anything. We're trying to find out what the definition of surface area is. Specifically, we want to know what a surface is. Okay, so we look up surface, and what is surface? A two-dimensional manifold. What is a manifold? Okay, we looked that up. It's a topological space that locally resembles Euclidean space near each point. Okay, so what is a topological space? What is a set of points? And what is a Euclidean space? Well, it says consists of points. So what is a surface? Well, apparently it's a bunch of points. I mean, that's what all this amounts to. It's just a bunch of points. What is a point according to Euclid? Well, we covered that in the past, and a point is a location. So a surface is a bunch of locations. So why don't we make the effort and define this scientifically? What is a surface in science, in physics? So here it goes, okay? Pay attention. Here's the definition of a surface for the purposes of physics/science, okay? That's it, folks. It's very simple. We don't need math. We don't need all this gibberish there. 3 or more locations on an object. Okay? If you have 3 locations on a sphere, you have a surface. If you have 3 locations on a plane, ideal plane, for example, again, you have a surface. Typically, in physics, which deals only with objects that exist, a surface is equal to the location of 3 atoms. Okay? So we're talking about the locations of 3 atoms that comprise the object under study. See how simple it was? 3 locations. That's it. That's what a surface is. Okay, now that we have a definition, maybe we can make sense of some things here. Okay, here's this fellow. It says a hypersphere has a 3-dimensional surface, okay, which curves into 4th-dimensional location. 4th-dimensional location. What is a 4th-dimensional location? What the hell is that? I thought location was a concept, and this person is talking about like that location has 4 dimensions. I mean, I don't know exactly what he means. He's got to clarify what a 4th-dimensional location is. As far as I'm concerned, location doesn't have any dimensions whatsoever. You can locate an object using 3 coordinates. That's how it's done in science, okay, in physics. And it says hypersphere is the 4-dimensional analog of a sphere, whatever that might mean, okay? No, here's in science, okay, you have a sphere has length, width, and height, 3-dimensional, very straightforward. There is no fourth dimension that we're aware of, but people are welcome to propose, first to draw another 90-degree line to those three there to show us that there is a fourth dimension, and give it a name. We need to find out what the name of that dimension is. Okay, and then that's got nothing to do with the location of the sphere somewhere in the universe. Okay, and for that we use these. They're known as coordinates, and they're known as longitude, latitude, and altitude. And they differ from dimensions in that they point towards the object. Okay, so coordinates point towards an object, whereas dimensions point away. It's facing, what direction the thing in question is facing or pointing to. Okay, so dimensions always point outwards, and coordinates always point inwards. Both are static concepts, and they have nothing to do with numbers whatsoever. That's in physics. Okay, we're talking about physics here. Okay, we don't talk about math, for example. And what do we do in science? Well, we have to define what the word location means. And here's the definition. Okay, we start with the word object. First word we have to define in physics is the word object. You can't do physics without objects. What is an object? That which has shape. Not that which you can touch, not that which you can see. Not all objects can be touched, not all objects can be seen. And we found that out by trying to see the sphere that the Klingon has there. We can't see it. Okay, so no, we can't use that. Space, that which doesn't have shape. Now we know what space is. It's that which doesn't have shape. It's the antonym of the word object. So we have object, that which has shape, space, that which doesn't. Distance is the space between objects. That's what we call distance. That separation, that gap. Okay, nothingness there, because what is space? That which doesn't have shape. So there is nothing there. Nothing in space are synonyms. Okay. And what is location? Well, it's the set of distances from one object to the rest. Okay. I like to synthesize that in a nice little saying distance is what lies between lengths. Okay? Length and distance are not synonyms in science, in physics. Okay? Length is what an object has, which is continuous matter from one end to the other of an object, and distance is what stands between two objects. They're not even remotely the same concepts. Okay? So distance and length are not synonyms. Not in science. In mathematical physics, they are. And that's why they run into trouble, because they don't understand the difference between length and distance. And the reason for that is that they don't use either one of those concepts. What they use in mathematical physics is distance traveled. Distance traveled. What they do, they unroll the measuring tape because they're interested in measuring. And so they don't have distance or length in mathematical physics. All they have is distance traveled. The amount of units that the tape unrolled. Okay, so if you unroll your tape, and you first have to create a standard, obviously, for example, the meter. And if you unrolled your tape 3 meters, well, that's the distance traveled by the end of your measuring tape. And that's the number that concerns mathematical physics. It doesn't concern physics at all. Physics, we have to define everything qualitatively. Okay. Okay, another comment made by this gentleman. Okay, it's good that he drove the analysis today, the lecture. A circle, so we thank him. A circle, open disk, closed disk is two-dimensional. Yeah, a circle is two-dimensional, no doubt about it. It's a plane. All planes are two-dimensional. Okay, except some of the planes that mathematical physics bends into the third dimension, like Riemann triangles and Lobachevsky triangles, which I covered a couple weeks ago. In all of the above shapes, the only ones that are objects is the cube and the sphere. And I'm wondering why, because he defined it as that which you can touch or see. You can't see an ideal cube, you cannot see an ideal sphere, and that's what the word cube and sphere refer to. They refer to, or allude to, perfect, ideal geometric figures. So neither a cube nor a sphere exists in real life. Again, in real life, everything's made out of atoms, and all atoms are, any structure that you build with atoms, it's going to be irregular. When you get down deeper, you can get to the atom, like the hydrogen atom, and you can say, was that a perfect sphere? Well, from our point of view, if you were just to look at it and say, well, that's a perfect sphere, because we see it like from a bird's eye perspective. If you were Atom Man and you go there and see it up close, well, our atom is a bunch of threads that weave the surface of the electron, known as the electron shell, the surface of the atom. So even at that level, if you were Atom Man, if you had God's eyes and you were, that close to the atom being a monster and you being smaller than the atom, right? You would see that it's not a perfect sphere either under that condition. So there is no such thing as a perfect sphere in the real world out there. A perfect sphere, a perfect cube, is only in our imagination, and we can only do it through a projection. We cannot have one out here, okay, a perfect sphere out here. Even if you do it with lights, in other words, a hologram, you won't have a perfect sphere. Okay, and so yeah, we can't. So it's just he says, just because something has shape doesn't mean it's an object. Well, for that you got to define the word object, and hopefully you will not use the see-touch criteria anymore. Okay, because it's indefensible. And here are very quick reasons why. A couple of them. This is back of the napkin kind of thing. It involves two objects. Whenever you see or touch, you're talking about something that's seeing, something that's touching. The object that you're talking in question, right? The target object. So you need two objects to define object, okay? With see and touch. Second, it's subjective. Did you really see that spirit move the curtain? And yeah, you were on drugs on that day. You were drunk, whatever. You were high. Very subjective. Objects we can't see or touch. There are objects we can't see or touch. Okay, we can't see the air. The air is made out of atoms. Is the air an object? Yes or no? Does it have shape? Yes, of course it has shape. Around our planet, it's a shell. It has shell structure around our planet. But if you want, then you can blow some air into a balloon, okay, and now it has the shape of the inside of the balloon, which is close to a sphere, you could say, if your balloon is spherical, right? So yeah, air can be shaped to anything you want. And the question is, what is the shape of air? No, that's the wrong question. The question is, does air have shape? Anything made of atoms had better have shape. You can put it in any container you want. If you put it in a bottle, it has bottle shape. Okay, it has shape. What is the shape? We don't care. Does it change from second to second? We don't care. The point is, it has shape. Okay, we could color code it so that you can see it inside the bottle, inside the balloon, or around the earth, and then you'll know that it does have shape. Seeing and touching are verbs, and you always have to define the word object before you define the word motion, verb, right? Because motion is two or more locations of an object. Right? So the object has to move, and if it moves, you better have an object to start out with. You can't have motion without an object, which is what mathematical physics has. They get rid of the object and they start using points, and what are the points? Locations. So they move locations. Okay. So what do we do in science? Well, we define the word object, okay? And why? Because you need what is known as the golden principle of physics, which is you can't do physics without an object. Okay? What would there be to study without an object? What would be happening? What if God wiped out all the objects in the universe except himself, unless he's a spirit or whatever, okay? So he wipes out all the atoms, everything out there, every atom. There's nothing left there. So what is happening? Assuming you're a spirit next to God or God himself, what is he staring at? There's nothing in front of him. He wiped out everything. So what is God staring at if there's nothing in front of his eyes? What is happening? So yes, you need objects to do physics. And we separate that or contrast it with space. Okay, space is that which doesn't have shape. An object is that which has shape. And objects then we can point to. We point to objects, okay, and name them. So we say chair, tree, rock, house, whatever, dog. Concepts we define. Okay, so you have to define what a concept is. Energy is not an object. You have to define the word energy because it's a concept. Okay, and that's why I always say the definition of the word object destroys all religions. And that's why this person is trying to see if he can keep the see-touch criteria, because the definition of object, meaning that which has shape, destroys his religion. He realizes that, so he's desperately trying to go into panic mode, into what is it called? He's trying to fix it, somehow, because his religion falls there. That's why. Okay. What else do I have here? Yeah. Okay. We're gonna move towards again finding out where we started. Where is the Tesseract? Okay, we're moving in that direction. Please have patience. We got to go through this because we got to find out what a surface is, what an object is, these kinds of things we got to take care of first and show what's wrong with the definitions that we currently have for sphere, for, again, for surface, for location, for all these things, these terms, okay? Okay, so where do we start? Well, we start with the word point. Again, we need to know what a point is, and this is what it is for mathematical physics. This is the notion that's out there. This is the notion that they put into what is known as geometry, and what you'll find out that none of what follows now is a geometric figure. That's the bottom line. And so we have the word point. Let me put this up here first, okay, so I get this, so you can see what they're referring to with all this, okay. Give me a second here. There he goes, okay. And so we have context there. We have the mathematicians. What is a line for them? Well, it's a bunch of locations, what they call points, or which they represent pictorially with points, okay, with dots. So do not confuse the dot with a location, which is the real notion of the word point. And here you see it. A point is a primitive notion that models an exact location. What is a primitive notion? It means that it's undefined. Now, they don't want to define it because they can't define it as a location and then put a dot in there, because the dot belongs to physics. It's two-dimensional, and a location is dimensionless and is a concept. So is the point the concept, or is the point the object used to represent it pictorially? That's the question. And it says there, a point is a zero-dimensional mathematical object. Well, I don't know what a mathematical object is. In physics, we only have objects. We don't put any qualifiers in front of the word object. And there is no object that is zero-dimensional. And that ends the word point right there, okay? The mathematical machinery used to deal with points can be surprisingly slippery. No kidding, okay? Wolfram Mathematics, bastion of mathematical physics, it says a line is a straight one-dimensional figure. Well, I don't know about a one-dimensional figure. There's no such monster in science or in physics or in the real world. So I don't know what they're talking about. I don't know if it's straight, but for sure it's not one-dimensional. There's no such object as one-dimensional. And just in case you said, well, maybe they meant something else, they clarify, says, having no thickness and extending infinitely in both directions. There is no object that extends infinitely. There is no object that has no thickness. That is one-dimensional. And then it says a line is uniquely determined by 2 points. What was a point? It's a zero-dimensional mathematical object, meaning it's not an object. And so I don't know how they construct a one-dimensional line with zero-dimensional points. And what they're really talking about is locations, and what they're talking about as far as the line is concerned is an itinerary. And there you see the little turtle on the lower right, okay? Just walking along one step at a time, one location at a time. They continue, it says the notion of a line is usually left undefined. Oh, a so-called primitive object. Why do they leave it undefined? Why don't they define it so we know what they're talking about? Why don't they say, well, we're talking about location, and this is the definition of the word location. Why don't they do that? Simple. One advantage to this approach is the flexibility it gives to users of the geometry. No kidding. And then they put this notion down there at the bottom. It says all definitions are ultimately circular in nature. Talk about the fine print, okay, these disclaimers. And Wikipedia ends its notion there, it's an article saying a line may be interpreted as a geodesic. Shortest, what? Path. They're talking about a path. They're talking about an itinerary. They're not talking about a line between points. Okay? So yeah, all of geometry in its entirety, so-called geometry, what mathematical physics does, none of it is geometry. None of it has to do with objects. I mean, if they want to do measurement, they want to do calculations and angles and all that stuff, hey, be my guest, knock yourself out. But don't tell me any of what you do has anything to do with physics. Physics deals with the figures. And not one of the names used, like point, line, and so on, used in mathematical physics refers to a figure. It refers only to itineraries, locations, which they call points and lines, which only has the only purpose or the effect is to confuse you. Okay, because people think they're talking about geometric figure, and what they're talking about is itineraries. And that's what all of relativity specifically is founded on, itineraries. And we're going to get to that in the coming weeks. But just now, I just want you to keep that in the back of your mind, that these people are not talking about geometric figures, like when they talk about space-time. What are they talking about? Itineraries. They're talking about motion. They're talking about location. But they use words that sound like geometric figures, points, lines, circles, etc. Tesseract, right? to talk about them when none of those are really geometric figures according to mathematical physics. Okay, so let's start here. Just a quick review. This is what a circle is for the purposes of physics. Okay, I'm sorry, for purposes of mathematical physics. A circle is just a bunch of locations. That's all it is. It's an itinerary. It's known as an orbit. Okay, that's what they're talking about. They're talking about a perfect orbit. There's a center. You got a string, a rope, chain, whatever. The object is at the end of that rope, and you swing it perfectly, conserving the same center all the time. And so the object has all these locations, and that's what they call a circle. All the locations of that ball or cube or whatever you got at the end of your string. So they're talking about locations. They're not talking about a geometric figure. Okay, that's what a circle is for the purposes of mathematical physics. Okay, so what is a semicircle? Once again, here it is. Semicircle is this. It's half a circle. So you swing your ball or whatever you've got, like, in my case here, I got this ball, so I swing it around, okay? That's what a circle is, but the semicircle is just half a swing. And you stop it halfway, okay? Now you take that, and with that, you're going to build a sphere. What is a sphere? Well, you're going to twirl that itinerary, that geodesic around somehow, okay? And here it is, you twirl it around, okay? And that's what a sphere is, just a twirling around of a geodesic. Okay? That's what these people understand by sphere. Okay, so now that we know that it's just a bunch of itineraries and swinging itineraries and so on, let's get down to the tesseract, which is more or less the same thing, but not quite. There is a small difference. See, what they did just now is they moved an itinerary. They moved motion. Let's make sure we understand that, okay? We had something, which they don't identify because they're not concerned with some things. They have all these locations that made up what? The semicircle. Okay, so we have locations. We're not talking about an object. We're not talking about a line, which is what sounds in people's mind. They say, oh, a line, like a little stick. No. It's not a curved stick. It's not a straight stick. None of that at all. What it is a bunch of locations. Once they map that, they're going to twirl the locations around, a set of locations. And with that, they're going to build this thing they call the sphere, which is a bunch of locations which are twirling around. That's known as motion, and now they're going to move the motion around. Okay? The tesseract is something even weirder. They're going to move time around. They're going to twirl time around. Okay? And here it is. Okay? So let's go slowly with this so that you understand each point. Tesseract, also known as a hypercube, is a four-dimensional cube. Well, not really, because look at that. This is what this fellow says. Okay? And you look at that, no, it's got length, width, and height. It's got 3 dimensions, what I see there, and that's what it's called the tesseract. So I don't know what he's talking about. I mean, maybe his eyesight fails. He can't see the sphere or the cube that the Klingon has, but and I can justify that because he can't see that far, gazillions of miles away. But this, you should be able to see, right there. It's in front of your eyes. It's objective, right? What do you see there? You see 2 nested cubes, you could say, a special type of cube. One that's got these lines connecting the vertices, okay, vertex. But what you see in front of you has length, width, and height. So no, that hypercube is not a 4-dimensional cube. It's a 3-dimensional nested cube. That's what we have in front of us objectively. It's in projection, remember. Really, it's 2-dimensional, the one we're seeing. But we're understanding what they're trying to say here. They're saying, look, you got to look at this as a projection. Okay, it's projection in 3-dimensional, in a 3-dimensional background or platform. Okay, and yeah, that's what we have. 3-dimensional cube, double cube, you could call it. Okay, so no, the tesseract is not a 4-dimensional anything, or a cube, or whatever. And it says, it is the extension of the idea of a square to a 4-dimensional location. Again, I don't know what that means. Locations are not 4-dimensional. Okay, so locations are dimensionless. Okay, so we have to define the word location so we know what it is. No, location is a concept, and concepts are not made of dimension. They don't have dimensions. Take any concept you want, energy, mass, time, any concept you want. It has no dimensions. What is it? What does it have? Length, width, and height? Those are the 3 dimensions. So I'm not sure what dimensions location could have. Okay. It says that a cube is the extension of the idea of a square to a 3-dimensional location. Again, Locations don't have dimensions. What a tesseract really is, okay, that one there is static, and so you say, well, yeah, I know what that is. That's a three-dimensional nested cube. But that's not the notion they have for a tesseract. Tesseract is an expanding 3D cube. That's why time is involved. See those vortex there that unite the corners of each one of those cubes, the one on the inside, the one on the outside? That's time, okay? That's motion in the sense of expansion of that little cube to the big cube. That's what is represented there, okay? So tesseract is a concept that says a cube is expanding, okay? That's what the word tesseract stands for expansion of a cube. And I showed this the other day. This is my tesseract so that you understand what we're talking about here, okay? And there it is in graphic mode. You have a cube that is expanding. Okay, and what they do with that, they build these two nested cubes, which they represent the small one and the big one only. And they represent the intermediate ones with arrows or with lines or whatever. So when you see that cube that's there on the far right side, okay, underneath the red arrow, well, those are two nested cubes, but those lines that connect the corners of those two cubes, those are to represent that little cube is expanding. Okay, so it's like a photograph of a movie where they only show the first frame of the movie and the last frame of the movie. But the nonsense doesn't stop there. It continues, and you can see it on the left-hand side of the black region there. You can see the cube is expanding, becomes a hypercube and a super macho hypercube. Okay, so now they're going to take that super macho hypercube, which is a frame that includes the first and the last frame. They're going to superimpose those two cubes. And now they're going to twirl that movie that's synthesized in one frame. They're going to twirl that one around, okay? And that's what when you see a hypercube that's rolling in space, that's the nonsense that these folks are representing, okay? They're representing two nested cubes, which is really a cube that's expanded. You freeze that image with the inner cube and the outer cube only, not showing the cubes in between, right? And then they're going to twirl that. And what they end up doing is really twirling time, because what unites those corners of those two cubes is those sticks, those lines, they represent time. It's the expansion of the inner cube to fill the outer cube, okay? And here you see it. I've illustrated this so you can see what a tesseract really is, okay? First, we're going to expand the cube. Here it is, okay? So you can see the cube is expanding. Okay, and the little cube becomes the big cube, and they just represent the little cube and the big one. They just take the first and last frame of that, and they say, okay, that's a hypercube. Well, a hypercube is a movie. It's that entire movie synthesized in one frame of another movie. They just take a snapshot of that, superimpose it, do a little collage there, very selective collage. They only take the first frame and the last frame, okay? But again, the nonsense doesn't stop there. Here it goes. Okay, here's what they're going to do. They're going to twirl that thing now. Okay, so now they freeze that image. They're going to twirl time, because remember the lines that unite the inner and outer cube represents the expansion of the little cube all the way to the big cube. And then they're going to twirl this. So they're twirling time. And mathematicians are so used to twirling time that they've lost complete track of what they're doing conceptually. Okay, they don't even know anymore what they're doing, because they're moving time around. And you say, but is time a physical object? Can you move time? Can you move 2 seconds from here to there? And they go through, well, no, let me explain. There's nothing to explain. They're trying to move time. And here they illustrate the motion of time. Okay, so you say, well, what is time? Is time a physical object? And for that, you have to go to the sources, okay? And here's one source. It's from space.com, okay? Space.com, okay, here we have it, an article that pretty much synthesizes what time is for relativists, for mathematical physics. Okay, it says, what is time? Albert Einstein showed that time is an illusion. Oh, that's a good definition. What is time? That's an illusion. Okay, thank you. I always wanted to know what time is. Others say it's what a clock measures, other nonsense that people say out there. They just copy and paste. They don't even know what they're saying. Okay, it is relative. Relative? Relative what? It can be it can vary for different observers depending on your speed through space, or maybe through the drug that you took. I wonder what speed they're talking about here. Okay, what's that got to do with what time is, with the definition of time? Because the article is called "What is Time?" So finally, I wanted to know what time is. They say, "Well, it's an illusion." Well, I didn't understand that very well. That's not very illuminating. I didn't understand that. What do you mean by that? Well, it says it depends on how fast you go through space. Well, I still don't have a definition of what we're talking about. What is time? That was the title of the article, okay? To Einstein, time is the fourth dimension. Okay, another, so it's a what? It's an illusion. It's how fast you go through time. It's the fourth dimension. We still don't have a definition. I still don't know what time is, okay? It says space is described as a three-dimensional arena which provides a traveler with coordinates such as length, width, and height. Now, those are not coordinates. Those are known as dimensions, not coordinates. Showing location. Yeah, location is determined by coordinates, but again, those are not coordinates. Those are known as dimensions, but people don't understand the difference between dimensions and coordinates. Coordinates refer to location. Dimensions refer to the facing and the pointing of the tilt that an object has with respect to the rest of the universe. And it can only point in through three mutually perpendicular dimensions. Okay, that's different than the location of the object with respect to the rest of the matter in the universe, or with respect to three specific points. And again, those coordinates have to be at 90 degrees to each other. Okay, that's why we have names for them. Okay, time provides another coordinate. No, time is not a coordinate. Time is a number line. That's what time is. It's a number line, not a coordinate. Number lines and coordinates have nothing in common. Number lines have magnitude, and what they lack is direction. Time does not have direction, neither does any number line. You can point the number line any direction you want because it doesn't have direction. You can make it upwards, sideways at 45 degrees, doesn't matter. Number lines don't have direction. And second, number lines are not perpendicular to anything because they don't have direction. Okay, and on the other hand, dimensions have those two features. They have direction and they're perpendicular, perpendicularity, orthogonality. They have those two features. Okay, and that's why you can't put a fourth perpendicular dimension because you cannot even imagine such a monster. There's only three possible orthogonal directions in which dimensions can point or face, and you cannot have a fourth perpendicular dimension to that. That's why they never illustrate that. They usually use this space versus time, and they put the three dimensions as the word space in one line, and against them they put time. Like if time had a direction perpendicular to space. What sense does that make? But that's how mathematical physics does it. Okay. And it says time provides another coordinate, although conventional direction, which it doesn't. Although conventionally, it only moves forward. Well, which way is your forward? Because my forward is, I think, opposite to your forward. So, if for you time goes forward, for me it goes forward in that direction. For someone else, time goes forward in another direction. Forward is not a direction. Forward is a reference in which direction you're pointing. In other words, it's not a direction at all. There is no such direction known as forward. Your forward is opposite my forward. And so time doesn't go forward at all. Forward has to do with, again, if you're using their terminology, forward has to do with space, in which way you're pointing or walking or whatever. And time has nothing to do with direction at all. So what they could mean by time moves forward, I have no idea whatsoever. Okay, so what happens? Because of that, they end up with this. If I can put this up here, put it over here. This is from that article, and they say the following. Say, picture a four-dimensional fabric called space-time. No, I cannot picture that because space is nothing and time is a concept. Nothing is also a concept for that matter. But, I mean, so far we have concepts. We don't have an object, so I cannot picture it, and much less if it's four-dimensional. Whatever four-dimensional is, please draw it, and then we'll know what it is. And hopefully it's four-dimensional, okay? That means that you have four mutually perpendicular dimensions there, okay? I know of three. Please show us the fourth one, okay? That's perpendicular to the other three. When anything that has mass sits on that piece of fabric, it causes a dimple or a bending of space-time. What the hell are they talking about? Bending of two concepts? Well, here it is. Here's what they typically show, and you'll see that for both space-time and the Tesseract here, okay? Let me put it over here. And so they continue. It says the bending of space-time causes. They're gonna cause something. They're gonna cause objects to move. So they're saying if you bend this concept known as space-time, which they represent with a fishnet, if you bend it just by putting another concept in it called mass, if you bend it, they say that it causes objects to move. So the cause, the reason, or cause really, that the mechanism for why objects move, according to these people, is that space-time causes them, triggers them, pushes them, or pulls them, or whatever, to move. That's what they're saying. They move on a curved path, and that curvature of space is what we know as gravity. Okay, so this is what they teach these folks at the monastery, I guess. Okay, both the general and special relativity theories have been proven with GPS satellite technology. They've proven this. They prove that there's a concept called mass that can bend, warp, okay, whatever, comes in contact with a concept called space-time, which then causes objects to move on a curved path. That's what these people are saying. Okay, and they say that this has been proven. I'm not sure how they can prove it if you cannot even imagine. How can you prove something you cannot even imagine or you cannot illustrate? And they continue saying astronauts are time travelers. What is that? They return to Earth younger than their identical twins that remain on the planet. Oh man, we should travel more often, out there in space so we all become young again, the fountain of youth, I guess. General relativity provides scenarios that could allow travelers to go back in time. Back in time. How do you go back in time? I mean, I don't know how they do this. Maybe a good shot in the arm of some high-level drug. I don't know how you can go back in time. So they say it's according to NASA. The equations, however, might be difficult or to physically achieve. No kidding. Yeah, I doubt that you can go back in time and prove it with a physical experiment. Maybe with equations you can do that. I don't know if you can do that in the lab. Build a time tunnel, a wormhole or whatever. Okay, and the same thing happens here. Okay, and this is known as the hypersphere, and it's the same thing as the hypercube or tesseract, in the sense that what you're seeing is a sphere expanding through time. And there you have a static example and a dynamic example, okay, which they use to show how space-time or the Big Bang expanded, okay. And that's what it is. This fellow says a hypersphere has a three-dimensional surface which curves into a fourth-dimensional location. Again, I don't know what that is. A hypersphere is the four-dimensional analog of a sphere. And yeah, what they're doing is, remember what a sphere was? A sphere was the twirling of what? A bunch of locations. So we have twirling of the locations. Now those twirling of locations, once you freeze that, you make a movie with all those little locations. Okay, and they're expanding. They have more distance with respect to the first sphere, first twirling. And, you take only the first and the last one, I guess, for the hypersphere. And I don't know what they're united by, but whatever they're united by, that represents time. So you have an expansion of a sphere, like if you blew a balloon and you take the first and the last images, you kind of make a collage or you superimpose one upon the other, and you say, okay, this is my hypersphere, and then I guess you can play ball with that and you move time around as well. That's what a hypersphere is. That's what these people are talking about. Unbelievable. Okay, so here is follow up on that, which is the icing on the cake, as I call it. One pellet says, the Tesseract concept, blah, 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 blah. I thought the first guy started saying the Tesseract is an object. So is the Tesseract an object or a concept? Which is it? All of the above? Here we have relativity treats it like an object. Okay, that's what I say. Mathematicians illustrate this object as two nested cubes. I just showed that, and you can see that if you freeze that image, you have two nested cubes. They put it in motion on top of that. So what they're illustrating is an object, because I can see it's got shape. And that's the definition of an object, that which has shape. And it has shape, whether I see it or not, by the way, okay? But that's one way of, showing that you're saying that you can see it, okay? I can't see the one the Klingon has out there, but I can see this one, okay? That's why we have to distinguish objects from concepts in physics. We have to know the difference between an object or a concept, because here you have one guy says the Tesseract is a concept, the other guy said, no, it's an object. So who's right? Well, the only way we're going to find out is defining the word object and the word concept. That's how we're going to find out. Okay? He who cannot know the difference between an object and a concept is not a physicist. He's a religionist. He's a mathematical physicist or a spiritualist or whatever you want to call them. They're not physicists. Okay? They're not even scientists. Okay, and so here are my conclusions. Math figures are not figures. Math phys only has itineraries. Line, circle, etc., semicircle, whatever, okay? Bunch of locations, triangles, squares, same, okay? And also, for that matter, spheres, okay? All math solids are hollow. There's not a single mathematical figure, which is first that is a physical object. Then even if you put something there, draw something and illustrate it, whatever they illustrate, they say it's hollow. They're only talking about the surface, about the membrane, you could say, that covers a sphere, the membrane that wraps around a cube or a cone or a cylinder. They're not talking about a solid, they're talking about a hollow. Okay? Tesseract, what is it? It's two-nested cube if you just look at the image. Okay? Objectively, what you have in front of you is two nested cubes. That's it. But Tesseract, conceptually, what they're trying to really represent there is an expanding cube, which is a concept. Okay? Because now we're talking about, according to the definition of concept, a word that invokes or embodies two objects. Well, here you have two objects essentially, okay? Because you take the first and the last frame. It's like if you had two different objects, they're nested, one is superimposed upon the other. That's a concept. So the tesseract, which you point to, which is two nested cubes, if it's just what's in front of you objectively, that's an object. But the other one, the notion of an expanding little cube that turns into a big cube, that's a concept. So these people have to decide what a tesseract is. Is it the first one or the second one? Okay. And then mathematicians are spinning time when they spin a tesseract, because those sticks that unite the two atoms, those are what? That stick represents time. The time it took for the little cube to become the big one.